About reference systems. This is something that you will see throughout the school. It's an important aspect because you will get mapping products that are already more or less put together for you. But in real time, in real life, you have to do it yourself or someone has to do it for you. There are some reference frames that are considered when you're looking at planetary data, and this typically is due to the fact that we are obtaining data from spacecraft orbiting. And these spacecraft, they of course, they're in a certain position compared to Earth, compared to antennas. Their bus or the spacecraft itself is pointing at the surface to take pictures, and all of it actually has to come together. In fact, it's complex. I would say it's a rocket science because it's extremely complicated, and there are many things that are playing a role, including the accuracy of where your position in the solar system, the accuracy of the speed and the position of your spacecraft around a certain body, the accuracy of the angle between, I don't know, your axis of spacecraft and the object on the surface that you want to image. So all of it, in fact, is complicated and is taken care for you or for us by professionals doing science operations and mission operations. But at the end of the day, we have to live with it. And the consequence of inaccuracy, which is obviously there, is that sometimes your imaging is not exactly fitting where you want. That's a problem that on Earth you really don't see anymore, but on planets you do see. And there are many ways this can be taken care of. Typically, it's transparent to you, and you're not really seeing the effect of it, but it's there. And you should be aware that, of course, errors in pointing or errors in positioning or errors in orbit determination and timing are there, and they have an impact on the quality of your geometric data that you're using as base map. And Ricardo, in a couple of tens of minutes, will show you something about that. This, of course, can, in this very basic example, mean just mismatch of different images taken by either different times or different spacecraft. But obviously, this can be minimized more or less a posteriori, or with the proper calculation of the pointing of the experiment. Now, the map-wise or GIS-wise, some of you already are very familiar with it, some of you maybe less, but there are many definitions around. A map projection, of course, is a model like a geological map is a model of the subsurface and the surface. A map itself is a model of the surface in terms of geometry. And of course, you also need to have a reference body because it's not like a Cartesian plane. Typically, we're talking of irregular bodies in the worst case, or like things that are close to a sphere or a spheroid. All of it at the moment and during the school is going to be done via computers. So of course, it's using software systems. And the most common software system to deal with geographic data is a GIS. There are many implementations in the last decades. The one we chose is an open source one. You will hear also about that in a moment. Reference surface can be various, can be variable, but at a very basic level, they can be a simple geometry like a sphere or like a rotational spheroid, or can be a bit more complex. On Earth, obviously, one can refer to the geoid, which is common. This can also be done on other planets, for example, on Mars or any other body where you have a good information on the shape of the body and you can model its gravity field. But in certain cases, such simple geometries are not enough. And that's the case for minor bodies. That's the reason why in the last day of the school, we are using specialized tools to do this. Time-wise, we should really not worry, but obviously when something is changing, like plate moving or surface changes that are relatively strong, this also has an impact of what you see. We consider it not really having a big impact at the moment, but just be aware that somewhere else, like on Earth, can be important. So at decades of difference, the absolute position of things on Earth can change quite a lot. As we said, the map projection is a model. Specifically, it's a model of putting something which is not natively 2D into 2 dimensions. So essentially, projecting onto some sort of plane or surface what is on the surface of a body, which is, as a first approximation, a sphere. You can classify map projection by their reference body geometry. For example, if you want to draw what's on a sphere onto a cylinder which is touching at the equator, your sphere, you can use a cylindrical cluster of projections, and so on and so forth. You are not limited to a single geometry. Of course, if you're using a cylinder, you are touching the equator or a certain line on a sphere or spheroid. If you're using a cone or a plane, you are touching either, again, a line or a single point. But the point is that depending on the reference solid that you're using to project your original body, you have different properties. And these different properties reflect in different things that are more or less respected or more or less deformed on your map. In this very simple example, you see on the top left a cylindrical equidistant, on the bottom left a cylindrical equalarium, and on the right a Mercator. And if you look at this kind of vertical orange things, on the top left map they have the same length, then below the upper one, the one to the north, is shorter, and funnily enough, on the other map is the other way around. Now, obviously, this is creating problems. When you read the map, it's typically this has been taken care of by someone. But when you are doing it yourself, you have to consider what's important for you. You are mapping shapes, while then you want something which is keeping the shape and the angles as much as possible. You are mapping surfaces, then the surface has to be kept, and so on and so forth. And if you do this exercise over and over, you can identify certain properties that you may want to keep not too different from what they are in reality on your map. So your model has to be more or less fitting and respecting one or more of these parameters. Obviously, there is no free lunch, which means that you cannot have that easily everything faithful to reality, and then you have your map. That's why you have a wide range of maps. These resources I really invite you to go through. Again, this presentation is not for you to just look at it. I made it for you to explore it and to look at the sources, because this can be very helpful when you have any mapping problem or you look for solutions. And of course, on Earth, things are reasonably easy because we have a very well-documented, well-known surface. This is not necessarily the case for other bodies. This is an example that actually you will use in your hands-on. If you access yourself the presentation, you can navigate, you can move around. But you see that it's not quite a spherical object, but it's also not too far from it. In fact, I'm not sure if you can see it. There is a little red line that is cut into the body. This red line is not the pole, of course. It's just a random line that connects the center of the body to the outside. And more or less, it shows you that at the end of the day, you always cut the surface of your body with a single point. This is relevant because it means that if you're cutting the surface of your body with a single point, you can, model the position of any object on the surface with a pair of coordinates, spherical coordinates of latitude and longitude. And by the way, I think this sphere is about 580 kilometers. So the whole thing, the whole Vesta, you can put it inside a box or a sphere of 580 kilometers. But some of the radiuses are smaller. There is something that, of course, you need to be aware that there are different standards, and this can be annoying sometimes. Depending on the type of body, you can have planetocentric or planetographic or planetodetic, also called latitudes. And the difference is just with the planetocentric, you consider the angle between the equator and then the line that is crossing from the point on the surface to the center. In the other case, is just the normal to the point that you're considering that is crossing the equator. So typically, the planetographic is always higher than the planetocentric. So what is the issue with it? Well, of course, it's the issue that you may have, depending on the standards you're using, confusion. That's why, in many ways, what has been a de facto standard, at least for bodies that are not so different from a sphere, is just to use a sphere. Because obviously, if you're moving from a sphere, from a spheroid to a sphere, the planetographic and centric latitudes are just the same, because the normal at any point of a sphere is just pointing towards the center. But apart from that, there is an issue. We said that there is a unique latitude and longitude on Vesta. Well, yes, but if you're going to some body which is not that, so to say, regular, you start seeing, and if you wait a couple of minutes here, you will see that this line is not cutting a single point. In some parts of the comet, it does cut more than one point, which means that for an individual pair of latitude and longitude coordinates, you cannot identify a unique point on a body. This is a problem because obviously you cannot really use a normal map to map this. And there are many ways to address this problem. One way is what 2 years ago was developed by Björn Grieger, who was working at ESA and was working on the Rosetta mission, which is this QUAC, which sound, I don't remember the acronym. It's complicated, but you can click on the reference. And basically, it allows to map also bodies that will not be possible to map in a standard, so to say, spherical geometry fashion. And if you look on the upper left, you see this kind of green duck. It's like, you know, this kind of rubber duck that you make a bath with. But the red part indicates the areas where in the previous plot, you will actually cut the surface in 2 points, which means that you cannot handle a spherical coordinate as in other planets on, for example, on this comet. The same story you can play, and again, this is just for you to go look at the possible geometries of solar system bodies. This is Ryugu, where Hayabusa 2 was visiting. This is Bennu, where in fact Osiris Rex. You will have specific seminars on that in the next days. And moving on, that's Eros, where there was also NASA mission a few decades before. You see that the range of geometry is very wide, but the planetary, the planets and the large moons, they're all reasonably similar to spheres. That's why we can do the approach that we will do in the next 3 days on those bodies. And that's why instead this approach cannot be applied to the irregular bodies that are, of course, number-wise, the vast majority of the solar system bodies, whether it's Oort cloud or asteroid belt. Same Itokawa. Itokawa is very cute. You will see it sometimes modeled as a sea otter. If you add the mustache and the nose, I don't have it here, but I can find it for you. And also we're talking about a irregular body, which it's impossible to model as a single sphere. Now, when you're shooting projections, and we try to get a bit fast on that because we want to keep to the time, but obviously feel free to ask questions. As I said, you may use to keep certain parameters constant, like the scale or the shape or the distance, and there are ways to visualize it. One way is the so-called Tissot indicatrix. This kind of yellow circles, they give you an idea of the deformation of the surface in a certain projection. Now, this is just a map of the moon. As you will see it in white, you see the highlands, in black, you see the area, more or less like you will see it from Earth. And these yellow things are actually giving you a proxy of how deformed is the surface. I mean, you don't really need this to tell you that at the sides you will have high deformation and the center you will have less. But still, it's a semi-quantitative way to do this. And if you do the same exercise with another projection, in a case this is like a crop of equidistant cylindrical, you see that what is round at the equator is not round at the pole, which means also that in such projection you can expect your craters not to be round when you go up in the latitude, not because the craters are not round, they're also round, but your projection is deforming them. You will hear from Thomas and from Bagia later on that there are ways to handle these issues. And that's why also tools are very important. This is in case of Mercator. Mercator is very nice. You see, here you don't see any ellipse. All the circles, they are staying circles, which means that the shape of stuff is respected, but things are getting big. Now, think of like the maps you see on the web of Africa and Greenland, and then you wonder why Greenland is bigger than South America or is almost as big as Africa. Well, because of this. Because the shape is respected, but not the scale. Now, That's again a polar graphic. We won't use it in the school, but it's also very popular. And you can see that when you move away from the center, in this case the pole, but doesn't have to be a north pole, you can center it whatever, the scale is getting bigger. So you are overestimating the size of things if you're not taking precautions. Now, this is just a very simple way to show you the deformation that you can have between a kind of a view of moon from Earth, more or less, like an orthographic and the cylindrical. You see that at the center is not so much. You see Imbrium basin, it's a bit smaller, but more or less is the same. But if you move to the edges, you see that you're compacting half of the moon in just a small bit. So what you will see is that the extent of this, which are the extent of this, will have a significant deformation on the side. All these kind of multi-ring basins that you see at the edge here, of course, they are just compressed into a very thin segment around your circle, which is your orthographic projection. And if this is this kind of hemisphere, the other one will be, well, the other half. So you see, you have to consider when you are handling map data that they have deformations and you want to minimize them in the area that you're mapping it. Now, this is just a very small example. If you click on the presentation I shared, you can actually zoom in and do that's a web Mercator version of Ganymede. So here the scale is getting up towards the poles. This is instead an equidistant cylindrical, and it's funny because if you change the central longitude of the references, obviously you kind of pan your map around. This can be very handy. Obviously, if you are instead looking at the areas and you want to measure them, this projection is not right, but you should rather go for this one. But the geometry then is not really so respected. This is again an orthographic. If you look at Ganymede from the other side, it looks like that. At the end of the day, it's a matter of choice. And we are moving to the end. That's the Robinson, doesn't matter. These are all kind of standard projections that you will find one way or the other into your workflow while working on maps or reading maps that are published. Now, how do you choose projections? I mean, the projection can be just choose arbitrarily. Actually not, because typically the rotational state and the geometry of a body are dictating your projection. Here you see, and I invite you to click on this and have a look, the projection of the standard mapping of USGS of both base maps and geologic maps on Ganymede. And the point is that you can see that the projection on the equator will be slightly different from the projection on the mid latitudes and on the pole. And I can anticipate you will see in a second when we wrap up, that at the equator, you will have cylindrical-like projections, you will have conical at the mid latitude, and you will have a stereographic on the top. But why this? Well, because of course you're considering the axis of rotation. Theoretically, if you will ignore it, you could do something which is more of like a geodetic grid. So a kind of a more or less tessellation, regular tessellation of the surface. And I don't know, each of them could be a gnomonic or a stereographic or whatever, or a local Mercator. This could be a way to go. It didn't go this way, and that's the way life is. So at the moment, we are also living a lot with legacy. And the legacy is that projections are chosen depending on the rotational state of bodies, which means that close to the axis of rotation intercepting your surface, you will have polar stereographic or similar. You will have conical as best projection on mid latitudes and cylindrical projection at low latitudes. That's the case for Ganymede. That's the case for Venus. You just see that for Venus, there are more quadrangles. Why? Well, because Venus is big, so you may want to use another level of hierarchy when you're modeling your map. And that's Vesta. You will hear more from that by, it's very similar to Ganymede. In fact, you see the polar stereographic north and south pole. You have the mid latitude with the conical, and then you have the equatorial latitude with a single strip of cylindrical projection. I invite you to go through it and have a look because there are standards. The USGS and IIU have also data on that. There are relevant papers that are quoted in the references that I showed you. But at the end of the day, what you see on GIS system is typically something that is not necessarily following the standards of the IAU, but is following standards of cartography, which are more or less de facto or more practical. So just be aware that what you're using on a GIS may be different from the IAU standards from the certain body, and so on and so forth. I just wanted to point your attention to the repo that you have linked in several places. This is not really instrumental to the presentation, but there is some stuff that you may find useful if you're playing around with the projections. And what I think you will find useful, regardless, are the sources. So please have a look. If you have a question, reach out. We are at 10 sharp. Sorry if I was going a bit fast, but then we try to keep the time for the other speakers. Thank you so much. If you have questions, please dump them on Slido.